Third course of this school. We are very happy to have Matthias Gaberdiel from Zurich, who will tell us about two-dimensional conformal field theories. So please.
Okay, so thank you very much for the invitation. It's always very nice to be back in GGI. So I don't really have a good sense of what your background is. So I really need you to interrupt me when I'm boring you or when I'm going too fast. So please stop me, because I have absolutely zero idea of where I should pitch this lecture. So I'll pitch it somewhere, and then you have to recalibrate me. I have as you can see, I've brought a full folder, so there is plenty of material. So let's see how far we get. Okay, so what I want to do is give an introduction into 2D CFT. And I shall always assume to be dealing with the Euclidean quantum field theory. So obviously you could also discuss this in a Minkowskian setting, but that's not what I shall do. I shall always assume it's a Euclidean quantum field theory, so in 2 dimensions that will be a 2-dimensional Euclidean quantum field theory. So what does it mean to be conformal? Well, what this means, it's a quantum field theory in whatever dimension you are in, for me always Euclidean, such that it's not just invariant under the Poincare symmetry, but it has a bigger symmetry. It has the symmetry of conformal transformations. So what are conformal transformations? So conformal transformations are transformations that preserve angles, but not necessarily lengths. So Poincare transformations preserve lengths. So the norm of a vector is invariant under rotation, under the Minkowskian norm is invariant under a Lorentz transformation. So these things preserve norms, but a conformal transformation is not necessarily preserving the length scales, but it's meant to preserve angles between any vectors. So what does this mean in terms of the underlying metric? So if you think of you have an underlying metric, so in our case this will be delta mu nu, but I'll write it more generally as eta mu nu. So this will be the metric of my underlying quantum field theory. So if I change coordinates, then so if I go from old coordinates to new coordinates, so the metric would change in this manner. So if I was looking for Poincare transformations, I would be looking at transformations so that the metric is invariant. So this is the rho lambda component of this metric after the coordinate transformation. I mean, it's a tensor, so it transforms as a tensor. So if it was a Poincare invariant transformations, I would demand this to be the identity. But for conformal transformations, since I don't insist on length scale to be invariant, but only under angles to be invariant, I can allow for an overall factor. And so you see, this would just rescale the metric, but if you calculate the angle, it's the inner product of 2 vectors divided by the norms. That is invariant under rescaling the metric. So therefore, I'm allowing for the metric to be rescaled. And if I'm interested in conformal transformations, I'm allowing this in an x-dependent manner. So this prefactor that rescales the metric may not be the same all over my space-time. It may be different at different points in the space-time. So the conformal transformations are all the transformations that have this property. And the first step in understanding what a conformal field theory is to understand what's the group of conformal transformations. I mean, it's obvious that this is going to be a group, because if you compose 2 such transformations, then if the first transformation rescales the metric up to a scale and the second one does, then so does the composition. So this forms a group, and the first step in order to understand what a conformal field theory is to understand what's the group of conformal transformations. And in order for you to get a sense of so I'm obsessed by 2-dimensional conformal field theory, and you may ask why. I mean, the world seems certainly to be more than 2-dimensional, i.e. 4-dimensional. So why on earth should you be interested in 2-dimensional CFTs? Well, the world sheet theory of string theory, blah, 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 blah. But there's another, in some sense, much more fundamental reason for this. The conformal group in 2 dimensions is vastly bigger than in higher dimensions. And as a consequence, 2-dimensional conformal field theories are much more constrained by the symmetries than in higher dimensions. And in order to convey that to you, I first want to explain to you what the conformal groups looks like in a general dimension. I won't derive it. It's a tedious argument, and you can look it up in any of the textbooks. If you believe, I hope you believe me. If you don't believe me, then that's a bad start to these lectures. But it's not super instructive to go through the proof to show that these are all the conformal transformations. What I'm going to do, I'm going to write down a bunch of transformations. I'll demonstrate that they satisfy this property, and then I'll wave my hands to say that these are all, and I hope you believe me. And this is true. I will do this in general dimensions, and then I will explain to you what's special about 2 dimensions, and then we'll take it from there. Okay, so what are the transformations that leave this invariant? Well, first of all, they're obviously the Poincare transformations, because they do this with lambda squared being equal to the identity. So we have the translations. So I'll denote them by T, and this is simply x mu goes to x hat mu, so the new coordinate, and the new coordinate differs from the old coordinate plus a constant. So that's just a translation, obviously nothing happens. And I'll just note down how many there are of these. There are D translations because A mu is a D-dimensional vector. So I'm thinking of this now, doing this in R to the D. So in Euclidean D-dimensional space. And in Euclidean D-dimensional space, there are D different translations because you can translate in any of the D directions of your D-dimensional space. Okay, that's nothing too surprising for you. Then the next ones are equally unsurprising. There are rotations. Now, obviously, rotations. So if you were in Minkowski space, you would say this is the Poincare group. Then you would have Minkowski transformation. You would have the conventional space rotations, but you would also have the transformations that mix space and time. But because we are in Euclidean space, all of these are just what you would call rotations. Because in Euclidean space, time is just the same as space, so everything is a rotation. So in this language, this would be x mu goes to x hat mu, and x hat mu would be some rotation matrix r mu nu times x nu, and the rotation matrix is such, you see, then the condition would simply be that eta mu nu, r mu rho, r nu lambda, and what this means, if you think about this in terms of matrices, this is R transpose E eta R, and in order for that to be eta, that's the orthogonal group. So there will be a half into D minus 1 such transformations. So these are the familiar transformations you are familiar with from conventional Poincare invariant quantum field theory, and obviously these transformations are also part of the conformal group. The conformal group is more liberal. It's not more restrictive, so it allows for more, but surely it allows for these. Okay, so what else do we have? Well, there's one pretty obvious one, which is the dilatation. So what is dilatation? Well, you do the most naive thing you can do. You just take x mu and you map it to lambda times x mu, where lambda is a real number. So that gives you one transformation. And obviously, you're just blowing up space, right? You're making space bigger by a factor of lambda. Now, obviously, then this will exactly be lambda squared, right? Because the derivative here will just be lambda times the delta. This will be another lambda times the delta. So this will give you eta times lambda squared. So this will be an example of a conformal transformation, but it's a bit of a sort of simple-minded example of a conformal transformation. Okay, I mean, it's also obvious that that's a conformal transformation. Now, there's one more set of conformal transformations, and that is most easily described in a slightly roundabout manner. You see, these are all continuous transformations. They have a continuous parameter. There are D continuous parameters here. There are a half into D minus 1 parameters here, and there's one parameter here. The final conformal transformation I'll write down for you is a discrete transformation. It doesn't have a continuous parameter, but then I'm going to combine it with the other ones to give you another family of transformation that has a continuous parameter. So the final one is the so-called inversion symmetry. And the inversion maps x mu to x hat mu, and you defined x hat mu to be x mu divided by the norm squared of x squared. So what this does is it maps a point outside the unit sphere into a point inside the unit sphere and vice versa, right? It's a reflection along the unit sphere, right? Because, I mean, a point whose norm is bigger than 1 leads to a point whose norm is smaller than 1 and vice versa. So it maps the outside of the unit sphere to the inside of the unit sphere, the inside of the unit sphere to the outside of the unit sphere. Now, why is this a conformal transformation? Well, so let's check. So what we have to do is we have to calculate dx hat. So what is dx hat mu by dx rho? Well, so we take the derivative of the numerator. So this gives you, well, we have a 1 over the norm of x squared. And then we have a delta mu rho. That's when the derivative hits the numerator. And then the derivative can hit the denominator. And if it hits the denominator, it'll give you minus. So, I mean, it's, so I take the outer derivative. So 1 over x squared becomes minus 1 over x squared squared. And then the inner derivative will give me a factor of 2 times x mu times x rho. Right? Because if I take it, I mean, what's the inner derivative? This thing here, so if I take the inner derivative of x lambda, I mean, this is a x squared. Then, because it's quadratic, this is just 2 times x lambda, x rho. And this is just 2 times x rho. So if I, well, I have to be careful. If the indices downstairs, it'll be 2 times x rho upstairs, because I should have really written this as in this way. If I contract indices properly, so if I take the derivative with respect to the upper index, the lower index survives, and because there are 2 terms, I get 2 times x rho, and this I have to multiply with the x mu, so this gives me the minus 2 times x mu x rho term for the second term. Okay, so that is obviously this factor here. So then I have to work out what is the left-hand side. So what's the left-hand side? So I have eta mu nu, and then I have 2 of these guys. Now, it'll be convenient to rewrite this slightly by writing a factor of 4 here. And so obviously you're going to hate me for doing this, but given the blackboard is so small, I hope you excuse me for doing this from time to time. So I'm going to get a 1 over x norm to the power 4, but I have 2 such factors, so I'm going to get a factor of 1 to the x to the power 8, and then I have delta mu rho with the factor of x squared, so I have an x squared, which is this guy, times delta mu rho, minus 2x mu x rho, and then I have a x squared times delta nu lambda, minus 2x nu x lambda, right? I mean, this is just written out the left-hand side. So this is eta mu nu, and then for each of them, I've just plugged in this formula, right? So now if I evaluate this, what do I get? Well, so obviously not much survives. So the eta mu's, so this just becomes an eta mu nu. This becomes an x squared and x squared. So I get a term that looks like 1 over x to the 4 times eta rho lambda. This is from this term with this term. And then what do the other terms look like? The other terms look like plus, so I have a 1 over x to the 8. Then I have 2 terms, the mixed terms. I have minus 2 times the norm of x squared times, and now if I contract this, you see the indices just, so if I contract this one, with this one, then the mu becomes a nu, the rho becomes a nu, so this becomes a rho and a lambda, so this becomes x rho, x lambda. The other cross term also becomes 2 minus 2 x squared, x rho, x lambda. And then this term becomes plus 4 times, and then the x mu, x nu times eta mu nu gives me also an x squared terms. And then this x rho, x lambda just becomes an x rho, x lambda. Is that clear? So now you see the magic. Minus 2 plus 4 is 0. Very good. So this term disappears. And what we see is that this is indeed proportional to eta rho lambda, but the prefactor is 1 over x to the 4. So this is a transformation where lambda squared is 1 over the norm of x to the power 4. So it obviously depends on x. So this is an example of a sort of non-trivial conformal transformation. The scale factor isn't just a number. It depends on the position, and it depends on the position as 1 over the norm of x to the power 4. So that's a conformal transformation. But unfortunately, you see it's only a single one, right? There's no free parameter, so that doesn't give you a Lie group, right? A Lie group, you want to have continuous parameters. So this inversion is an isolated species. This is like a biologist going to the rainforest and finding a new single plant, but you somehow want to embed it in the sort of general picture of how plants are connected to one another. So you want to combine this inversion to give you more interesting conformal transformations. And the way you do is by defining what's called the special conformal transformation. And what you do is you combine the inversion with a translation. So what you do, we start with x mu, then we apply an inversion, so we get x mu over x squared. Then we apply a translation, so we get x mu plus a mu times x squared over x squared, right? I mean, I've just taken this and added the vector a mu to it, but I've brought it on a common denominator to write it as x squared a mu divided by x squared, and then I apply another inversion to it. So when I invert this again, what I have to do, I have to calculate the norm of this guy. So what is the norm of x mu plus a mu times x squared divided by x squared? If I calculate the norm square of this, because see, I mean, I have to, the inversion instructs me to take the vector and divide it by the norm squared of it. So I have to work out now the norm squared of this vector. So what is this? This is, I get the 1 over x to the 4 from the denominator, and then from the numerator I'm going to get an x squared term from this guy. Then from the cross term I'm going to get plus 2 times x dot a times x squared. That's the cross term, and then I have this term, and that gives me an a squared x to the 4. Right? So that's the norm squared of this, and obviously there's a factor of x squared which is common, so I can write this as 1 over norm x squared times 1 plus 2 x dot a plus a squared times x squared. Right? I mean, I just factor out, there's an x squared here, there's an x squared here, and if I calculate, divide by x squared, this becomes a square. So what I'm going to get is a 1 plus 2xa plus a squared x squared divided by x squared. So I have to take this vector and divide it by this. So then this x squared cancels against this x squared. And what I'm going to get is x mu plus a mu times x squared divided by 1 plus 2x dot a plus a squared times x squared. Okay, and you see, because I've composed this out of stuff that's conformal, I know that it's conformal. I don't have to check it again. You see, it wouldn't be much fun to do that calculation for that transformation. I mean, masochists among you may do that, it'll work, but I wouldn't want to do it in front of all of you in public on a blackboard, and I certainly wouldn't want to do it on a small blackboard of that size. But we know by construction that it'll be fine because it's an inversion, a translation inversion, so nothing could have gone wrong. And now we have a one-parameter family of transformation. You see, the reason is you have to do this is that the inversion is not part of the identity component of the conformal group. So you have to apply it twice to get back into the identity component. So you combine it with something in between. So you see, when you set a equal to 0, then obviously this becomes the translation again. So there's an infinitesimal transformation here encoded by a. Obviously, if you invert and you don't translate and you invert, you don't do anything because inversion is order 2. It gets you back. If you map from the inside to the sphere, to the outside to the sphere, to the inside of the sphere, you haven't done anything. So for a equal to 0, it's obviously the identity, but you get another infinitesimal family of conformal transformations. And if you count them, you get another d infinitesimal families because they're parameterized by this vector a mu. So altogether, unfortunately, I've run out of blackboard now. Let's see whether I can find the corner where I can, well, I guess I better go here. So How many transformations have I found? Well, I've just erased some, but so conformal transformations in d dimensions is a translation. There are d of those plus rotations, a half into d minus 1, plus dilatations 1, plus a special conformal transformation d. And all of them are sort of infinitesimally different, so they generate the Lie algebra of the conformal group. And if you add this up, you should get a nice number. So let's see what we get. We get a half times d squared. Then we get minus a half times d, plus d, plus d. So this is plus 3 over 2 times d, plus 1. And this is a half into d plus 1 times d plus 2. Right? Because it's a half d squared. Then I get 3d over 2, and then I get 2 over 2 is equal to 1. So that so what I'm assuming here, and that's the bit I'm not subjecting to you explaining, is that these are all the conformal transformations in d dimensions. That's something you can prove. It's a bit tedious, but there we go. But if you believe this, what you read of is that that's the number of infinitesimal conformal transformations. And then as a physicist or as any smart person, whenever you see a group and you see a dimension, you just look up the set of all possible Lie groups, and then you ask which Lie group has that dimension, then the answer is SOD plus 2. So that's the conformal group in d dimensions, in the Euclidean world. Now obviously if you do this Minkowskian, then the usual stuff happens, right? I mean, why is this SOD plus 2? Because somehow the eta matrix is in Euclidean space. If you do this in Minkowskian space, you get something like SOD plus 1, 1, etc. And if you do it in some funny signature, you split up the d plus 2 into pieces of the positive and the negative signature part of your metric. But that's the sort of answer in general d dimensions. The conformal group in d dimension is SOD plus 2. That's bigger than the Poincare group in d dimension, which is SOD plus 1, and that's what it is. Okay, so now, that's what's true in general dimension. So we can ask, what is the two-dimensional version of that? Well, we can first ask, what is the two-dimensional version of all of these transformations I've written down? And let's do this first, and then think about what other conformal transformations exist in 2 dimensions. Okay, so we are going to now look at 2 dimensions. And when you look at 2 dimensions, one of the facts that make this analysis nice is that R2 you can think of as being the same as the complex plane. And in the following, instead of working with R2, we will virtually always work with the complex plane, because in the language of the complex plane, it'll be much easier to understand what the conformal group is, etc. The structure is really analytic. I mean, part of the power of 2D conformal field theory is that it's really an application of a function theory, i.e. theory of holomorphic functions of one complex variable. And that has to do with R2 being essentially the same as C. Okay, so how many transformations do you have in R2, and what do they look like in the 2-dimensional setting? Well, the translations will just be the transformations Z. So the coordinate here I'll denote always by Z. And you can think of this as being x1 plus ix2. But I'll just think of it as a Z. So that the translation is Z goes to Z plus A, or Z plus B. Let's write it as Z plus B for funny reasons that will become clear in a second. And B will be a complex number. So this will be 2 real components. So remember, in D equals to 2, there should be 2 translations. 2 real translations the same as 1 complex number. So we have 1 complex number worth of translations. Now, how many rotations do we have in 2 dimensions? So we have half into 2 is 1, times 2 minus 1 is 1. So we have 1 rotation, and we have 1 dilatation. So rotations and dilatations in 2 dimensions really want to combine into Z goes into lambda times Z, where lambda is in general a real number, a complex number. You see, if lambda had modulus 1, then it would be a conventional rotation of the, but if lambda doesn't have modulus 1, then it's a dilatation. So in some sense, rotations and dilatations in 2 dimensions just want to combine into one transformation, which is rescaling Z by a complex number. So the rotation bit is if this complex number is modulus 1, and if it doesn't have modulus 1, then it also rescales the thing. Okay, so that's what rotations and dilatations look like. And then we have the special conformal transformation. We should have 2 of those. So let's look at this formula. What does this formula look like in 2 dimensions? So the special conformal transformation, what this looks like is Z goes to Z plus, and now I have to multiply. So, okay, so A is, let's call A C for a change. So C is another complex number, and then Z squared will be Z bar, right? That's the norm in Z squared. And then I have to divide this by 1 plus 2 times the scalar product of x with A or x with C. What's the scalar product of Z with C? Well, this will be a half into Z bar C plus Z bar, right? That's the way you define the scalar product, because you see, if you write this in terms of real coordinates, this would be x1 minus ix2 times y1 plus iy2, and then you do the antisymmetric bits, so you only keep the x1 squared plus x2 squared term. So the term that is in the denominator, the 2x dot A, will look like c z bar plus z bar c, and then I have a term that looks like cc bar. Right? So that's the special conformal transformation as written out in a sort of 2-dimensional complex formulation. And now if you stare at this formula, you see this formula has a very nice structure. You see this is of the form z into 1 plus cz bar divided by, and the denominator also factorizes, right? The denominator factorizes in 1 plus cz bar times 1 plus, oops, sorry, I've forgotten, there's a zz bar here as well, right? There is an a squared x squared, so this is the, what I call A, which I've now relabeled as C, and z squared, so there's a z bar, c bar, z bar. So you observe that the denominator can be written as 1 plus zz bar plus 1 times z bar z, right? So this is the 1. This term is this term, this term is this term, and this term is this term, right? So it just factorizes in the denominator. And now if you look at this, you see this term cancels exactly this term. And therefore the special conformal transformation in 2 dimensions has the form, this is equal to z over, or z over 1 plus z bar z. So that's z hat. So that's the special conformal transformation as written in this complex language. And now if you stare at this, you observe that these transformations precisely generate the Möbius group. So what is the Möbius group? The Möbius group is the group of special fractional linear transformations of the complex plane. In fact, there are the automorphisms of the Riemann sphere to themselves. So these conformal transformations generate the Möbius group and the Möbius group is Z goes to AZ plus B over CZ plus D, where A, B, C, and D may be taken to be element of SL2C. Now, so in particular, you see the first one corresponds to, so the translation just corresponds to the, so you can think of this as a matrix. In fact, the reason it's convenient to write this as a matrix is that if you apply a conformal transformation and then you apply another conformal transformation and you label them in terms of these matrices, then the combined conformal transformation will just be the matrix product of the two. This is another calculation for which the blackboard is too small, but that's another calculation you can easily do and convince yourself of. So you see the translation just corresponds to the matrices 1, B, 0, 1, right? They correspond to A and D want to be 1, C is 0 and B is 1. And then rotations and dilatations correspond to the matrix lambda, square root of lambda, 0, 0, lambda to the minus a half. And then the special conformal transformation corresponds to the matrix 1, 0, C1, or, well, it's C bar, but I mean, it doesn't really matter, right? It's just a complex parameter. I should mention here, you see, you may be worried, where does the determinant condition on SL2C comes from? You see, the determinant condition from SL2C comes from the fact that in order for this to be a conformal transformation, it has to be invertible. I mean, that's what I've always implicitly assumed. Otherwise, this lambda squared term would be 0. Then the metric would sort of collapse. I'm not allowed to do that. So this must be invertible. And if you write this down in terms of the matrix entries, what this means is that the matrix has to have non-trivial determinant. But you see, if you rescale A, B, C, and D by a common factor, then the transformation doesn't change, right? The transformation A, B, C, D, and 24A, 24B, 24C, and 24D is obviously exactly the same transformation because the 24 just cancels out of everything. And therefore, without loss of generality, you may as well assume that you've rescaled your parameters so that they have determinant 1. And then you see, this has the right dimension. Then you see there are 4 complex parameters. There is 1 constraint, so you have 3 complex parameters. And these are exactly, there's 1 complex parameter translation, 1 complex parameter rotation dilatation, 1 complex parameter special conformal transformation. At least it has the right number of parameters, and you can convince yourself that these transformations generate exactly this group. So that's the Möbius group. And why is this a natural group? It's, as I said, it's the automorphism group of the Riemann sphere. So if you take the complex plane, you can make it into a compact Riemann surface by attaching to it the point at infinity. Then you call it a Riemann sphere. This is a holomorphic, a Riemann surface, a manifold on which you have holomorphic charts. And then you can ask, what are the transformations of the Riemann sphere to the Riemann sphere that preserve the conformal structure? And the answer is the Möbius group. So the Möbius group is the global set of transformations that map the conformal, the Riemann sphere to the Riemann sphere, and that's what you find. And that's the 2-dimensional analog of what you have in every dimension. And that group will play an important role. These are the global conformal symmetries of a 2-dimensional conformal field theory, and they play a special role, as you will see later on. So this is an important part of the conformal group, but the reason why 2 dimensions is interesting is that is not all of it. There is much more in 2 dimensions, and that's what I want to explain next. But is this clear so far, or do you have any questions? Yes? Say again?
Do you mind repeating the argument you gave about rotation?
Well, so, I mean, rotation would be, the rotation would be z goes to e to the I theta times z, where theta is real, right? I mean, that's the rotation by theta in the 2-dimensional plane. And this rescaling would be z goes to rz, where r is real. Right, so this is the rotation, this is the dilatation, and if you combine them, it's r times e to the I theta, so that's the most general complex variable. Okay, so this is sort of the 2-dimensional analog of what's true in every dimension. That's the Möbius group. That's the group of global conformal symmetries. It has a very nice structure here. It's the Möbius group. Now, what's special about 2 dimensions? Well, what's special about 2 dimensions is that the world of conformal transformations is much, 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 much bigger. So why is it much bigger? Well, I mean, if you know, I don't know how much complex analysis you know, but you see the transformation, if you take any function z and map it to f of z, where f of z is holomorphic, then one of the things you know, or you learn in complex analysis, is that a holomorphic transformation preserves angles. That will preserve angles for any function f. I mean, formally, that follows, I mean, there are various ways of seeing this. You can write it, I mean, that satisfies the Cauchy-Riemann equation, and then from there you can read off that it preserves angle. But I hope, well, I'm not sure whether you've seen this before, but this is a true fact, and it's just the fact of complex analysis. So this means any holomorphic transformation is a conformal transformation, not just this sort of measly small set of Möbius transformation, anything goes. So the group of conformal symmetries in 2-dimensional is is infinite dimensional. Because there are infinitely many holomorphic fields, infinite holomorphic functions. So if you want to write this infinitesimally, you can say what this means is you can replace z, and it's convenient to say, well, it's always, if you think of this as acting on, so what you could say is you can add to it a function of z to the n plus 1, and that would be a conformal transformation, right? I mean, that's a holomorphic map. It maps z to z plus epsilon z to the n plus 1. Z to the n plus 1 is a holomorphic function. And if epsilon is 0, then it's the identity. And epsilon is small, it gives you a conformal transformation that's close to the identity. But you get one for every integer n. Right? So you don't have 3 generators. So you see, the conformal transfer, the Möbius group has basically 3 generators, namely the translations, the rotations, dilatations, and the special conformal transformations. And now here, we are going to have infinitely many. So what this means, we are going to end up with a Lie algebra. So the Lie algebra of SL2C, SL2C is grosso modo the same thing as SU2, right? It's a 2 by 2. Okay, so it's only determinant, not unitary, but who cares? It's basically a 3-dimensional Lie algebra. And so the Möbius group is a 3-dimensional Lie algebra. And the group of these transformations is a Lie algebra that has infinitely many generators. So it's what you would call an infinite-dimensional Lie algebra. And obviously, infinite is much more than 3. So you have much, 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 much more symmetries, local conformal transformations, then you have the global conformal transformations. Now, obviously, you have to be a little bit careful, and that's the reason why the Möbius group will continue to play an important role, is because you see, these things will have poles somewhere. I mean, the function z goes to z to the n plus 1 is not holomorphic on the entire Riemann sphere. It has a pole at infinity. Or if I take n to be negative, it'll have a pole at 0. So these are locally defined conformal transformations. They're not globally defined. And as a consequence, their implications for the structure of, say, correlation functions will be quite different for the global conformal transformations and the local conformal transformations. But if you just look at the world locally, what this tells you is you have infinitely many conformal transformations, and that gives you lots and lots and lots and lots of constraints, and that's what's the power behind 2-dimensional conformal field theory. Now you may ask, why on earth did I write this with this funny n plus 1 there? So why did I do this? Well, it has to do that I want to have a certain subalgebra. Well, you'll see in a second why I wanted to do that. But before we do that, let's understand how the Möbius generators fit into this. Well, the translation will be the generator where n plus 1 is equal to 0, where shift z plus a constant. So the translation generator will correspond to L minus 1. The rotation and dilatation generator, well, there you replace z by 1 plus epsilon times z. That will correspond to L0, right? Because if I set n equal to 0, it goes like, I mean, this will be the transformation z goes to 1 plus epsilon times z. That's sort of the rescaling, and therefore that corresponds to L0. And then the special conformal transformations, well, let's think about it, what they looked like. Probably I have erased it by now. So remember, they looked like z goes to z over 1 plus c times z. And if I expand this out, then what is this? If c is infinitesimal, that's the same as z goes to 1 minus c times z. So this is z minus c times z squared. I mean, plus, right? I mean, I assume that z is infinitesimal. And then if c is infinitesimal, then 1 over 1 plus cz is the same as 1 minus cz. I mean, it's just a geometric series. I just expand it out. So this is the first term. I ignore the higher order terms. I think of c as being infinitesimal. Okay, let's write it as epsilon. So maybe then you are happier. So what this corresponds to, you see, is exactly the term when n is equal to 1. So in this nomenclature, translations will be identified with the minus 1 generator of this translation, rotations and dilatations with the 0 generator, and special conformal transformation with the plus 1 generator. Now, why is this a natural way of parameterizing it? Well, it's a natural way of parameterizing it because we can think about what's the Lie algebra generated by these transformations. So let's work out what's the Lie algebra generated by these transformations. And the way you think of the easiest way of working out what the Lie algebra of such transformations is by thinking of this as acting on some set of functions as differential operators. I mean, if you have a set of functions that are, if you have functions f of z, and you have some symmetries acting on z, then g on this is defined as f of g to the minus 1 of z, right? I mean, that's the usual way in which the group acts on function. It acts on functions by pulling the rug under the function, right? You apply the inverse transformation to the argument so that the group transformation law comes out right, because I mean, you have to make sure that G1 after G2 is the same as first G1 and then G2, and therefore you have to have the inverse here. So what this means in terms of this transformation, when it acts on functions, what it means is that Ln corresponds to the transformation minus z to the n plus 1 d by dz, right? Because, I mean, if you shift the z argument infinitesimally by something proportional to z to the n plus 1, so if it acts on a function, the inverse of it would be z minus epsilon to the z n plus 1, and that's to first order produced by taking the derivative with respect to z and multiplying it by z n plus 1. That's just shifting the argument by a term that's proportional to z n plus 1. But now that we've written it like that, it's easy to work out what the Lie algebra is of these generators. In fact, that's always a useful trick. Whenever people tell you what the transformations are, in order to work out what the Lie algebra is, you let it act on some generic function space, and then you can just simply derive the commutation relations from this picture. So let's save some space and write this as minus z plus n d by dz. So now what we can do is we can work out what's the commutation relation of Lm with Ln. Okay, so now it's easy, right? So we first apply Ln, and we think of this as acting on some function f of z, but we're not going to write the function f of z anymore in the future, because it just acts as differential operator, and it acts as differential operator on whatever is to the left of it, sorry, to the right of it. So I first apply Ln, so this would mean I have z to the n plus 1 d by dz with a minus sign, and then I apply z to the m plus 1 d by dz, right? So this is if I apply Ln minus Ln, and then if I do it the other way around, I simply do it the other way around. Right? So now, obviously, when the differential operator hits to the right, it either goes through it, these terms cancel. So the commutator is when this guy hits here, and when this guy hits here. So what do I get? I get n plus 1 into z to the m plus n plus 1 d by dz from here, minus m plus 1 z to the m plus n plus 1 d by dz from here. That's the commutator, right? Can you see that? I mean, it's just, there's a term, it either hits here or it goes through. It hits here and goes through. The term where it goes through, they just cancel with one another because it's the same term. So the only term that survives if they hit the corresponding polynomial, and then they just bring down a power of m plus 1 and reduce the exponent by 1. So then you get n plus m plus 1 with a factor of m plus 1, and likewise you get n plus 1 with the power of z to the m plus n plus 1. And now, you see, you can write this, you see the 1 bit drops out, and you can write this as minus m minus n times z to the m plus n plus 1 d by dz. And therefore, you see what this is just m minus n times L m plus n. So that's the Lie algebra of the infinitesimal conformal transformation. It has this very simple structure. It's an infinite dimensional Lie algebra, and it has the form that the commutator of Lm with Ln is of the form m minus n times Lm plus n. And now you see why this choice is quite natural. You see, so in general, this is an infinite dimensional Lie algebra. If I take m to be 45 and n to be something, then I get something, right? I mean, all the numbers. But every now and then, it could happen that I sort of, these numbers m and n conspire that I can't go out. And you see in particular, that set of generators L minus 1, L0, and L1, they form a subalgebra. Right? I mean, if you take any one of them, if you take any 1, 0, and minus 1 and add it with 1, 0, or minus 1, you end among 1, 0, or minus 1, unless you take 1 with 1 or minus 1 with minus 1. But because it's a commutator, you see, if you take 1 with 1, you get 0, and if you take minus 1 with minus 1, you get 0. So the set of generators 1, minus 1, and 0 forms a subalgebra. And this subalgebra is precisely SL2C. This is precisely the subalgebra of the Möbius group. So that's how the Möbius group sits inside this bigger Lie algebra, where this Lie algebra is much, much bigger. This is, by the way, called the Witt algebra. Not the Witt algebra, not the Bernard de Witt algebra, but the Witt algebra. So it's called Witt algebra. It's the Lie algebra of infinitesimal conformal transformations. It's infinite dimensional, and that's the structure of it. And it simply comes from the form of how the conformal transformations act locally on the coordinates of a two-dimensional Euclidean, in a two-dimensional Euclidean space. Okay, is that clear? Now this algebra looks deceptively similar to an algebra many of you may have seen before, which is called the Virasoro algebra. So let me just explain to you I mentioned what the Virasoro algebra is, but the Virasoro algebra will play an important role this afternoon, probably, yes. So, well, maybe I will even start with it this morning, let's see. So the Witt algebra has actually an interesting central extension. So the central extension, and I'll explain to you this afternoon or maybe later, of the Witt algebra is the Virasoro algebra. And the Virasoro algebra basically looks like the Witt algebra. Except it has an additional term where this, for a physicist, this is a number. For a mathematician, it's a central element. So what this means, so you make the Lie algebra bigger by one generator. And this new generator you call C. And C has the property that it commutes with everybody. So it's what's called a central, so this is called a central extension. And central extensions, so central extensions is the euphemism for anomaly. I mean, what this means is that this is something that isn't quite a conformal symmetry anymore. I mean, this is the conformal symmetry as it comes out of the book. And this means it has sort of gone a little bit broken, but it's been broken in a super minor way. It's just been broken by the fact that there's a number that sort of messes up things in a fairly benign manner. And the reason why this is important is that, as we'll see this afternoon or maybe already later, that when you look at quantum field theories that have the conformal symmetry, they will typically have an anomaly. They will have a conformal anomaly in that the conformal transformators will involve this central term. This central term will appear. This is not something which I dream up to annoy you. This is something, if you look at the simplest example of a conformal field theory in two dimensions, and we'll do this later, namely the free boson in two dimensions, you'll find the way the conformal symmetry generators act in the quantum theory has this term where this number has a specific value, which you can compute, and we will compute it this afternoon. So this is something that is a quantum property of the quantum field theory, and the way we will see that this comes from the fact that when you quantize the theory, things stop commuting with one another, and there's a normal ordering term, and the normal ordering term is responsible for this. So this you should think of as being an H-bar correction to your classical symmetry. So your classical symmetry is broken by this term, but it's broken in a very controlled manner, such that you can still use the power of the conformal symmetry, despite the fact that, literally speaking, the conformal symmetry is broken. So that's the reason why this is called the central charge. Sometimes it's called the conformal anomaly. What it means is that in the quantum system, the symmetry is slightly deformed, and it's deformed by this term. And as I'll also explain to you, you may ask, why on earth do I write down this term in this funny manner? And the argument is, it is necessarily of that form. And that has to do with Lie algebra cohomology. That has to do with the fact that up to suitable redefinitions of the Lie algebra, you can always bring any central term into that form. In fact, you may ask, why has nobody ever told me about central terms before? I mean, when you discuss quantum mechanics, you have the group SU2. You can ask, why are there no central terms in quantum mechanics? I mean, there's also quantum effects. Why are there no H-bar corrections for SU2? And the answer is, the Lie algebra SU2 doesn't allow any central terms. I mean, you can write down a central term, but that's just your decision of writing down bad generators. You can always absorb the central term into redefining generators. For the Virasoro algebra or the Witt algebra, you can't. There is one freedom that you can't undo by redefining your generators, and that allows you to bring it always into this form. And that is something that you can't get away by redefining your generators. It's a true anomaly. And that has to do with the fact that the Lie algebra cohomology of the Virasoro algebra, the second cohomology of the Witt algebra, is non-trivial, whereas the second cohomology of any of the Lie algebras you've encountered in your life so far are all trivial. They don't have any central extensions. So that's the reason you have never seen them before. But once you get into the realm of slightly more complicated Lie algebras, like this infinite-dimensional Witt algebra, the second cohomology is not trivial. Central extensions appear, and then by Murphy's law, what can appear will appear. So, I mean, look, there is a possibility for a quantum effect to lead to this term. You would have to be extraordinarily lucky not to pick up that term, and generically, you're not lucky. But you pick up a very definite term, and for the free boson, that's the reason why you normalize it that way, this number will be equal to exactly 1. For the free fermion, this number will be exactly equal to a half, and for other conformal field theories, it'll be equal to many other numbers you can pick up in your life. This number can be worth many, many things, but it's a parameter that classifies in some sense the conformal field theory because it tells you the amount by which the conformal symmetry is broken by quantum effects. It's a feature of your conformal field theory. It's a characteristic of your conformal field theory. It tells you in which way the conformal symmetry is broken in the quantum theory. But I'll explain that in more detail later on. I just wanted to highlight that this is, you've probably seen the Virasoro. I mean, how many of you have seen the Virasoro algebra before? See, here we go. But how many have seen the cohomology of the Virasoro algebra before? Okay, so then I'll explain that, and I'll show you that you can bring it into that form, and then we calculate it and see what we get. Okay. So now, so this is sort of abstractly on the level of symmetries acting on the space of on the space-time on which the theory lives. Now, if I have a quantum field theory, I can ask, what does this mean in terms of the stress-energy tensor? So now it depends a little. I don't think I really want to go deeply into this, but in a quantum field theory, so the next 10 minutes will be slightly sketchy. It will not be really crucial for the rest of the lecture, so I'll just want to sort of say a few things so that you've heard them, but I don't necessarily want to go into the details of it because that would take me another 3/4 of an hour to explain in detail, and it's probably not worth it. So in a quantum field theory, you have the stress-energy tensor, which you can define, for example, for a scalar theory, the stress-energy tensor would be something like d nu of, so if your Lagrangian density just depends on the scalar field, then the stress-energy tensor would be just this, where L is the Lagrangian density. This is the stress-energy tensor of some quantum field theory, say a scalar quantum field theory. And then you sort of know that the transformations, the stress energy tensor induces the local coordinate transformations. So if the theory is invariant under the transformation x mu goes to x hat mu, which is equal to x mu plus epsilon times omega mu of x, then what this should mean that T mu nu omega nu is conserved. So, I mean, there's a little bit of a calculation that lets you go from one to the other, but roughly speaking, you see the stress energy tensor induces coordinate transformations, and if the theory is invariant under that coordinate transformation, then the current that corresponds to that coordinate transformation must be conserved. I mean, I can derive this if you want to, but this is really, would be more of course in QFT rather than a course in CFT, and it won't play an important role later on. So let me just say it, and let's not get deeply into it. So you see, I just want to motivate what this means, what the conformal symmetry means for the structure of the stress energy tensor. Well, you see, if the theory is invariant under translations, that means you can take omega nu to be a constant. So this would mean that d mu t mu nu a nu is equal to 0. And this must be true for all a nu's that are constants. So the translation invariant just means that the stress energy tensor is conserved. So this is true even without conformal symmetry. Whenever you have a translation invariant theory, then the stress energy tensor is conserved in this sense. And that simply comes from the fact that the stress energy tensor induces the coordinate transformations in that manner. So now, in our case, for a conformal field theory, we have the translations. So the stress energy tensor is conserved. And then we have the rotations. So what does rotations mean? Well, for rotations, x mu goes to x mu plus epsilon omega mu nu x nu, where omega mu nu is antisymmetric. This is what the infinitesimal rotations look like. So what this means is that you know that d mu t mu nu, d mu t mu nu, and now I have to contract this with omega nu rho x rho is 0. So a rotation invariant, so I know already that it's translation invariant, so d mu t mu nu is 0, omega nu rho is a constant matrix to first order, but it's antisymmetric. So what I learned from this is that this implies that omega nu rho times t mu, so I have, okay, so I have, so if the mu hits here, this is the only term that survives. So what I learned from this is that t mu nu omega nu mu is equal to 0. But because omega nu mu is antisymmetric, I can write this as omega nu mu times a half into t mu nu minus t nu mu. And this must be 0. So what you learn from the fact that it's invariant under rotation is that t is symmetric. So this is simply true for any scalar theory, even in, that's Poincaré invariant. If it's invariant under rotation, the stress energy tensor is symmetric. If it's invariant under translations, it's conserved. Now, what I want to aim for is to read off what it follows from the fact that it's invariant under dilatations. So if it's invariant under dilatations, then I can replace x mu by x mu plus epsilon x mu. Right, that would be the dilatation. And then what the corresponding transformation will be is that the conserved current is, So then what's the conserved current that's conserved? It's T mu nu x nu, right? This is the transformation, and then what you learn from that is that T mu is equal to 0. So, and that's the special feature about a conformal field theory. The stress energy tensor is not only symmetrical and conserved, it's also traceless. So what this means is T is traceless. And this is normally what people say. The reason I want to say this is that it's often what you hear in a conformal field theory. What's special about a conformal field theory from the point of view of the stress tensor of an arbitrary quantum field theory is that the stress energy tensor is traceless. So it's traceless, it's symmetrical because it's invariant under rotations, it's conserved, and it's traceless. And therefore, in 2 dimensions, there are not that many components that survive. So in 2 dimensions, I mean, how many components do you have? You have you have a T00, T01, T10, and T11. These are the 4 components in 2 dimensions. And because it's symmetrical, these 2 things are equal to one another. And because it's traceless, these components are negative of one another. So we have a T00 minus plus T11 is equal to 0, and we have T10 is equal to T01. So this comes from the symmetry, which comes from the rotations. The tracelessness implies that this is true. So what this tells you, there are only 2 components. There are only 2 independent components in 2 dimensions. And it'll be convenient to write them as T plus plus. Well, I'm probably going to get this wrong now, but to write them as this, and the other one as, but which one is which one, I will not. So it'll be convenient to write the 2 components in terms of complex combinations of this guy and this guy. I mean, there are only 2 real components, and therefore, instead of having 2 real components, I can write a complex component and its complex conjugate. So this is just to motivate what we'll just see in a second, namely that in the simplest example of a 2D conformal field theory, the stress energy tensor will indeed be traceless. We'll see this explicitly. And it'll be convenient to introduce these 2 components. And these 2 components will turn out to be the generators of the conformal transformations that we've just described. Okay, so this is sort of the abstract piece or stuff I wanted to explain about the conformal group in 2 dimensions. And what I would like to do next is to look at a simple example, and the simplest example is the free massless bosons in 2 dimensions, and see, I mean, this is now an honest quantum field theory. It's a very trivial quantum field theory, so don't fool yourself into believing that all conformal field theories are that trivial as that one, but let's at least understand one trivial example first before we get much more complicated. So 2D conformal field theories are rich. There are zillions of interacting theories, so it's not at all free. But in order to understand the structure, let's understand the simple toy model first before we try to get too fancy. Okay, is that clear? Is that, yes?
Why does special conformal doesn't play any role in
Yeah, so that doesn't lead, I mean, there isn't more constraints than that. So that's, yeah, it gives you a linear combinations of these constraints. I mean, there aren't more constraints than these. Yeah, it's a good question. But you see, in some sense, it's, I mean, you know, the special conformal transformation come really from the inversion and the translation and the inversion. So somehow, in the inversion, be a discrete transformation doesn't seem to give you anything more. But that's what it is. So that's what you get. And you see, you can't really get that much more. I mean, you've already cut it down to 2 components. I mean, at some stage, there must be something left. Otherwise, the theory would really be truly trivial. Okay, so after this sort of general, so now we know what we are looking for. We are looking for the Witt algebra or the Virasoro algebra. So if I write down a quantum field theory that's conformally invariant, we would expect to see the imprints of this symmetry appearing, and we want to construct the Virasoro algebra out of this quantum field theory, and then we want to calculate the value that I've just erased of the central term. That's an intrinsic property of this quantum field theory. So the simplest example is a free massless boson. So this is really as simple as it goes. So the Lagrangian density is just a half into, and because we're in Euclidean space, I mean, I'm just going to write it out sort of in the most pedestrian manner possible, so that there is no confusion about, I mean, that's the Lagrangian, right? So it's as trivial as it goes, right? I could also write this as a half times d mu phi. And because the metric is the Euclidean metric, raising and lowering in indices never costs anything. There are only plus ones. There's never a minus one. So I could have equally written it with downstairs. Doesn't matter. And mu runs over 0 and 1. There are two dimensions, the 0 direction and the 1 direction. So that's the kinetic term. I could write on a mass term, but it's not difficult to see the mass. You see, the mass introduces a scale. The scale will not be happy with scale transformations. So it'll be, that theory is in fact conformally invariant. Okay, so let's understand what this theory looks like. So first of all, what's the stress energy tensor? So let's see, so I just told you what the properties of this stress energy tensor should be, so let's just work it out. So the stress energy tensor in this case is d mu phi. So it's, so where did I write it down? It's the d nu by d lambda mu nu. So it turns out to be d mu phi minus a half times delta mu nu d phi squared. So d mu phi. So the 0, 0 component is what? Well, the 0, 0 component is d0, and then you have to subtract minus a half times d0, d1. So what this turns out to be a half times d0 phi, minus d1 phi. So that's the d0, 0 component. And then the d1, well, let's leave that here. So the d1 component is the T11 component is, so you get d1 minus a half, so this will just be a half times d1 phi minus d0 phi, right? Because it's d1 phi minus a half times d0 phi, d half phi, d1 phi. So now the d1 phi term comes with a plus sign, and the 0 phi comes with a minus sign. And you obviously see that this plus this is equal to 0. So this is indeed traceless as advertised. And then the other two components are just T01, and D01 is just going to be D0 phi, D1 phi, and obviously that's going to be the same as T10. So this realizes exactly, so it's obviously symmetrical, and it's traceless because this component and this component add up to 0. And now, as I already advertised before, it's convenient to introduce complex variables. So what we'll do is we'll define Z to be x1, x0 plus I x1, and Z bar to be x0 minus I x1. And then d by dz will be d by d0 minus I times d by d1, and d by dz bar will be d0 plus I d1. And then it'll be convenient to define the components t minus minus, and the t minus minus component is a half times t00 minus I times t01. So what is this? This is a quarter times, so it's a half times this half, so we have a quarter times d0 phi minus d1 phi. And now I have no space here anymore. So let's just write dz is d0 minus I d1, and dz bar is d0 plus I d1. So that's this piece, and then I have minus I times t01, and t01 is d0 d1. And if I take a half of it, and I've taken out a quarter, then I have a factor of 2 here. So I have a d0 phi d1 phi. And now what you spot is, there should be a factor of a half here, I guess. I think I want to introduce a factor of a half. And then this is going to be equal to, this is exactly equal to dz phi times dz phi. Because if you write this out, dz phi is a half, so this gives you a quarter. This will be d0 phi minus I d1 phi times d0 phi minus I d1 phi. And now you see you get, oops, sorry, now I've, yeah, so here I've written the indices downstairs, here I've written the indices upstairs, but you know, upstairs, downstairs, it's all the same, where Euclidean doesn't matter. So I probably should have written the indices upstairs here, but I hope you see. So you have the d0, d0 term, you have the d1, d1 term that comes with the minus sign, and then you have this term and this term you have twice, and they come with a minus I. So the t minus minus component you can write as dz phi. And then likewise, the t plus plus component you define by the effectively complex conjugate of it. So t plus plus we define as a half times t00 plus I t01. So you see the only thing that changes is the sign for the term that's proportional to I. So this minus 2 wants to become a plus, and then you see you obviously have to change the signs here. So this will just therefore be dz bar of phi. dz bar of phi. So these are the two components of your stress energy tensor written in these complex coordinates. So instead of looking at T00 and T1, T01, I look at T++ and T minus, and they are defined by these expressions. Okay, so these are the components of the stress energy tensor. And now what we need to know is, so we want to see that it's conserved. So what does conserved mean? Well, we have to work out what the equations of motions are. What are the equations of motion that come from this Lagrangian density? So the equations of motion are simply d mu phi is equal to 0. These are the equation of motions that this free scalar field theory has, right? Because you take the derivative with respect to d mu phi, and you take the d mu derivative of that, and that should be equal to d lambda by d phi, but there is no phi dependence, there's only d mu phi dependence. And what this equation means, if you write it out, this is just the equation dz bar of phi is equal to 0, right? Because if you multiply if you write this out, this is just d0 plus I d1 times d0 minus I d1 on phi is equal to 0, and that's nothing but d0 phi plus d1 phi is equal to 0. So the equations of motions are simply that dz bar of phi is equal to 0. And now we see what happens. You see a t++, because it's a dz bar derivative of phi, d of t++ will be equal to 0. So what we learn is that d of t++ is equal to 0 by the equations of motion, because if the d hits, by d I mean dz, right? The dz hitting here, it either hits this term or it hits this term, but in either case, by the equations of motion, it will be 0, and correspondingly, dz bar of t minus are equal to 0. So in a two-dimensional conformal field theory, you always end up with two components of the stress energy tensor. One will be a holomorphic function because it will be independent of z bar, and one will be an anti-holomorphic function because it will be independent of z. And these are the two components that survive after you've imposed the tracelessness and the symmetry. So this is true generically in a 2D CFT, but here in the example of the free massless boson field, you can see this very explicitly. Okay, is that clear? Okay, so now what we're going to do is we're going to solve this quantum as a free theory. So this is like, I mean, you all know QFT, right? Or you've been exposed to QFT. So the free scalar field you've probably seen many times. So we can just do the usual prescription that we always do. So what we do is we write down the most general solution, and then we declare the parameters that characterize the solution to become operators, and then we impose canonical commutation relations and then quantize the theory and get, okay, so let's just do that. So obviously, even here we have to do some work. It's not all free. Even in 2D CFT, from time to time, you have to do some work. Okay, so if you have to find out what's the most general equation of motion, well, what's the equation of motion? Well, you see what this means is that the most general solution, phi, if I write this in these complex variables, will be a function phi left of z plus phi right of z bar. Right? I mean, this is like the wave equation, right? So if you have dz bar of something is 0, then the most general solution is something that is either purely left moving or purely right moving. So what this means is dz bar of phi left is equal to 0, and dz of phi right is equal to 0. So when I say it's a function of z, and this is a function of z bar, what I mean by it that it's not a function of z bar, and this is not a function of z. So saying it's a function of z bar means that the z derivative is 0. Saying it's a function of z means the z bar derivative is 0. If something has the property that the z bar derivative of it is 0, then it's a sum of something that only depends on z plus something that only depends on z bar. It's just like solving the wave equation in any dimension. Okay, so that's the most general solution. It'll be something that is purely holomorphic and something that's purely anti-holomorphic. And then we just make a mode expansion for these guys. So phi left of z we write as a half times q. And then, so now, I'll come to that in a second. There's a little bit of there's a log term, so there we have to be a little bit careful. And here there are funny factors of I and square root of 2 and stuff, but don't worry. This is just convenient for reasons that will become hopefully clear relatively soon. So I make this mode expansion for phi left, and then for the phi right, I make a similar mode expansion, except now everything is a function of z bar. And I write everywhere bars, but I could have written other symbols. I mean, this is nothing, I mean, this is just the nomenclature. So that I call them A bar doesn't mean that they are the conjugates of A. They are not. A and A bar, I mean, I could have written them A left and A right, but common notation is that you call them A and A bar. So what I've done here is I've basically written down any power of z. I mean, okay, that's what I can do. Obviously, the z to the 0 term is this guy. But then I can also write down a log term, right? Because if I take a derivative of a log, I get 1 over z. So there's a log term. But with the log term, I have to be careful, right? Because this function is meant to be a good and honest function on the complex plane. So log z is not a good function on the complex plane. But phi is the sum of phi left and phi right. So as long as I add these two terms with the same coefficient, I get a term that looks like log z plus log z bar. And log z plus log z bar is log of z bar. And log of z bar is a good and wholesome function because z bar is real. And then as you go around, nothing bad happens. But that tells you that this coefficient wants to be the same as that one because otherwise you have a funny branch cut as you walk around your complex plane. But other than that, I've basically allowed for arbitrary coefficients. So P is an arbitrary coefficient, Q is an arbitrary coefficient, and the A ends and A bar ends are arbitrary coefficients, and that's the most general solution. I've just written down the most general function of z, holomorphic most general function of z bar, and just impose that it's single valued on the complex plane by insisting that this coefficient is the same as this, but these coefficients are whatever they are, right? I get a solution for any choice of an and a bar n. They needn't be complex conjugates of one another. This can be a complex field and so on. Now, if you see what enters here in the definition of t minus minus, it's really the z derivative of phi. And what enters in t plus plus, it's the z bar derivative of phi. So what we want to calculate is the z and the z bar derivative of these expressions. Okay, so what happens when we calculate dz of phi? And remember, so here z and z bar are being treated as independent variables. So instead of having x0 and x1, we think of them as being z and z bar are independent variables. Now there is a thorny issue here which is super confusing and you have to get over it, which is z and z bar are, at the end of the day, will be complex conjugates of one another. Z is x0 plus ix1, z bar is x0 minus ix1. And if x0 and x1 are real, then z and z bar will be complex conjugates of one another. So you may be confused about how I treat z and z bar as totally independent variables, because they are sort of independent, but they're also sort of dependent, because at the end of the day, they are complex conjugates of one another. Now, what you do in conformal field theory is you treat them as independent variables. Full stop, no questions asked. And what this really means is that you're going to the complexification of your two-dimensional real surface. You're not thinking of x0 and x1 necessarily as real variables. So you really want to treat z and z bar as totally independent variables. And you postpone it to the end of the course, which I will never reach, to impose the fact that z and z bar are complex conjugates of one another. So at the end of the day, So the strategy here is a little bit destructive. I want to sort of pick at pieces. For the pieces, I'm going to treat z and z bar as totally independent. And then at the very end of the day, I have to put the pieces back together to give me a real conformal field theory. And at that stage, I have to worry about the fact that z and z bar are complex conjugates of one another. And I will worry, except like always in this, you'll never reach that stage in your lecture, you'll never reach that stage in your review article. So this is one of the dirty little corners of 2D CFT nobody ever talks about. But at the end of the day, you have to put it back together so it becomes real. Now, actually, it's not true that nobody ever talks about it, but it's in chapter 17. But for most of the analysis, it plays very, very little role. So get it out of your head that z and z bar are complex conjugates of one another. Ultimately, they will be, but for most of what we're going to do, we just think of them as independent variables, and the justification is that we're really working with a complexification of our two-dimensional space. And in the complexification, there is x0 and x1 are complex, then z and z bar are not related to one another at all. So we go sort of off-shell in this space, we go to the complexification of our space, and only at the end of the day, we insist that it makes sense of the real slice, but that's for another day, certainly not today, not tomorrow, probably not even any time. But maybe I'll get to it. Okay, so we treat z and z bar as independent variables, so what we are calculating is dz of phi, and then obviously because z and z bar are independent, that's the same as dz of phi left, because phi right is a function of z bar, so it doesn't contribute. And then when I take the derivative of q, the constant term obviously doesn't contribute, and I get minus I over 2 p over z. And then I get plus I over square root of 2, the sum n not equal to 0. Then I get a minus sign from the z to the minus n. The n comes down, cancels the 1 over n that's conveniently standing there, and it gives me an an z to the minus n minus 1. And then you see that this really wants to be combined. This term really plays the role of the n equal to 0 term. You see the n equal to 0 term wants to go like z to the minus 1. I wants to go exactly like that. So we say that a0, we simply say 1 over square root of 2 a0 is p over 2, right? And then this simply becomes minus I over square root of 2 sum over all n, an z to the minus n minus 1. right? I've simply absorbed the first term into it, and what this means is that A0 is p over square root of 2. This is just, I mean, so there's a bit of housekeeping that I don't have to write this separate terms. I mean, here, obviously, I can't write the term with 0. I have to write a log, but once I've taken the derivative, it sort of groups itself together nicely. And then, so, okay, so that's what d phi z looks like, and then what does t minus minus look like? Well, t minus minus is d phi, dz phi. So there'll be 2 of those, right? So we get a minus 1 over 2. I over square root of 2 times I over square root of 2 gives me minus 1 over 2. And then I have a sum over n and m. And then I have an, am, z minus m minus n minus 2. And these we're going to write for reasons that will become clear soon as the sum over, probably with the minus sign. Let's see, yeah, with the minus sign. Sum over n in z. ln z minus n minus 2. And ln may remind you of something, but that will be, we'll see this in this afternoon. So what is this? I mean, we've just reorganized our sum. You see the terms where n plus m add up to a given number are the terms that contribute to this ln. So the ln consists of all the terms with a factor of a half. So the half goes into the definition of L. The minus sign stands outside. And then here, what I'm going to do, I'm summing over L, an minus L, al. I'm summing up all the pieces where the mode numbers add up to n. These pieces will be, they will go as z to the minus n minus 2. So Ln is the combinations of all the bilinears whose mode numbers add up to n. So that's the formula for the Ln generator, whatever that is. I mean, obviously, you can tell by the nomenclature that that will turn out to be the generators that satisfy the Virasoro algebra, but we don't know yet. At the moment, they are just generators defined by expanding out one of the components of the stress-energy tensor in terms of the modes that appear in the general expansion of the field. And then obviously you can do the same thing for the right movers. So the things that are dependent on Z are conventionally called left movers, and the things that depend on Z bar are conventionally called right movers. So when I call left movers, I'm talking about things that are functions of Z. When I talk about right movers, I'm talking about things that are functions of Z bar. And you can see the functions of Z bar as just a carbon copy, right? The functions of Z bar will do exactly the same thing. So there'll be an analogous formula for the L bars expressed in terms of the A bars. And the only slight subtlety here is that the A's and the A bars, they're independent, except they're glued together at the zero mode. The zero mode is shared, but apart from that, they are independent. But you'll see the fact that the zero mode is shared is not a big worry. I mean, that we'll keep track of, but that will not cause much grief. Okay, so the next step. So my time. Oh no, I thought I have another 10 minutes, right? Okay, so I'm in Zurich standards where you teach for an hour and a half instead of. So now my body clock tells me I have to stop, but my body clock is wrong. So now what we are going to do is we are going to. Okay, so then I should have probably written down this formula for L bar. So the formula for L bar then takes the same form. And our aim is to understand the algebra that's generated by these LNs. But when I talk about algebra, what I first have to do, I have to quantize this theory, yes. So you're saying here? Yeah, I'm thinking of Z and Z bar as independent variables. I'm not treating them. I mean, you are saying in 2 dimensions the del Z of Z bar is 1 over Z bar is a delta function. But I'm here treating Z and Z bar as independent variables. So then you don't see this term, right? Because, I mean, what you have in mind is that Z bar is really the complex conjugate of Z. But here I'm treating z and z bar as independent variables because I've gone to the complexification of my space. And then the derivative dz of 1 over z bar is 0. So yeah, I may have to be careful when I put things together at the end of the day, but at this stage I'm treating them as independent variables. Okay, so now I have to, now we need, so the next aim is that we want to quantize this theory, and then we want to determine, so I mean, as I was arguing before, the stress energy tensor induces the transformations of my theory. So it's not implausible that the modes of these components of the stress energy tensor will have something to do with the conformal transformations I wrote down before. I mean, grosso modo, that's what you would sort of expect, right? Because as I said before, T mu nu omega nu induces the transformation associated to omega nu. So therefore, the modes of T minus minus will have something to do with the conformal transformations that I analyze. I mean, I didn't really tell you, but this theory is conformal, which you can relatively easily see because the kinetic term, I mean, I should have probably stressed this. The action is the integral of d to x, and then I had d mu phi, d mu phi. And you see that this theory is at least scale invariant, because if you rescale x by lambda x, then you pick up a lambda squared from here, and you pick a 1 over lambda squared from the derivatives. So this action is at least scale invariant, and you can actually show that it's conformally invariant. So we know that we are in the realm of a conformal field theory, and therefore we shouldn't be surprised to see traces of the conformal symmetry that I argued on general grounds for you before, and therefore it's not so surprising that something that induces these conformal transformations will appear. And what we will see in a second, or not a very long second, is that the commutator of Ln with the field phi will precisely induce z to the n plus 1 d by dz on phi. So this is sort of our first aim, to see that these generators on the field induce exactly the conformal transformation I argued on general grounds to be before. But in order to do that, what I have to do is I have to quantize this, so I can take commutators. So, I mean, okay, I could try to do this. So if I did this classically, what I would have to do is I would have to calculate the Poisson brackets, and then you would calculate a Poisson bracket of this generator with the field, and you would see that that will induce the corresponding conformal transformation. But I don't want to go into classical field theory and Poisson brackets, so what we are going to do, we are going to quantize it. I directly work with commutators, and the commutator of that mode with the field will induce the conformal transformation, and then we basically know that it has to satisfy the Witt algebra because of the property I showed you before, because the commutator of these derivatives is the Witt algebra. So, and then I'll explain to you that it needn't quite be the Witt algebra. It can have a central term, because I'm only checking it by acting as commutators on fields, and therefore a central term would be invisible, and that's how the central term will arise. But we'll see that as we go along. But what we have to do is now to quantize the theory. So how do you quantize a theory? Well, what you do is you impose equal time commutation relations. Now, in the context of Euclidean quantum field theory, it's a little bit tricky to think about what equal time means, because there is no time. I mean, in the world of Euclidean quantum field theory, there is just two directions, and so what you have to do is you have to basically declare what you mean by time. So you can say what you mean by equal time. And in this context, it's conventional and useful to think of time as being the radial direction. So this is what's normally called radial quantization. So what we are going to do is radial quantization. And this is basically to think of as the radius as being, to think of as z as r to the e to the I theta, and r will be thought of as being, log r is going to be thought of as tau. I mean, you want to think of this as being e to the tau plus I sigma, I mean, if you are sort of a bit familiar with string theory, that's sort of what this really wants to be, right? You have a map from the cylinder into the complex plane, and the tau direction is, so you have a cylinder. The tau direction of the cylinder is this, the sigma direction of the cylinder is this, and you map this to the complex plane so that sigma goes around like that, and tau goes like that, or rather, log r is tau. So the infinite past will be the origin, the infinite future will be out at infinity. So, and equal time will mean equal distance from the origin. That's, okay, you have to, I mean, when you want to quantize this theory, you have to say what time is, and there is not a canonical choice. It shouldn't matter. So you choose whatever is convenient, and here it's convenient to do it that way. So you treat this as the radial coordinate as time. And then what you have to impose is the equal time commutation relation. So you have to impose something like phi of r and theta. So I'm writing z as r times e to the I theta, and z bar as r times e to the minus I theta. And then you have to impose that the canonical commutation relation, the canonical commutation relation should be between the field and the time derivative of the field. So time derivative, because log r is tau, the time derivative is r times d by dr of phi of r and theta prime. So this is the momentum field, this is the position field, and you choose r to be the same, but they're sitting at different position in space. So they sit, say, here and here. They sit on a circle at fixed time, but at different positions in the space, which is the theta direction on your complex plane, and then you impose that this should be equal to 2 pi delta of theta minus theta prime. So this is the canonical, I mean, as you know, quantizing a theory, even in quantum mechanics, you make a postulate, and the postulate is that I declare that that's what should define my quantum theory, that the fields I have should have the property that the field times the time derivative of the field should satisfy this commutation relation, and then I plug in this mode expansion and read off what this means for the coefficients, and in the process the coefficients become operators because they satisfy commutation relations. And again, I'm not sure of you, but you've probably seen this before. It's a bit tedious to go through this calculation in detail, but do you want me to go through this in detail, or are you happy to just me quoting the answer? I mean, you probably know the answer anyway, so why should I kill myself deriving it? So if you plug this in and you treat them as all independent, what you find is that AM with AN would be equal to m times delta m minus n, and AM bar with AN bar will equal to m times delta m minus n, and the a's with the a bars will be 0. So this set of commutation relations, once you plug this in, is equivalent to this set of canonical commutation. I mean, this is what you know from, you've seen this probably in string theory before. I mean, this is just some tedious expansion and then picking the different terms and checking that it's that these are the commutation relations that guarantee you that. And then, so this is what's for the A's. Now, obviously, A0 will commute with everybody, right? Because there's a factor of m here. So, I mean, A0 can only not commute with itself, but obviously the commutator of A0 with A0 is 0. So you ask yourself, what's the partner of A0? And the partner of A0 is Q. So the non-trivial commutator for A0 or Q is that the commutator of Q with P is I. So that's the additional commutator that you need, because I mean, here I've only given you the mode expansion, the commutators for the A's, and then the P's and the Q's satisfy this mode expansion. Okay, so these are the commutation relations, and then, like with any treatment of quantum field theory, you're going to construct the Fock space of states, and the Fock space of states will be constructed by considering some ground state that will be, so you declare some of these operators to be annihilators and some of them to be creators. So this is just like in normal quantum field theory. So the AMs with M positive are the annihilation operators. And the AMs with, and likewise for the M bars with M less than are the creation operators. And then the Fock space of this quantum field theory is basically all the negative A generators acting on some ground state. The ground state will be characterized by a number k, and k is basically the eigenvalue of A0. So the convention is that P on k is the square root of 2 times k on k, or put differently, A0 on k is just k times k. So this bracket labels the eigenvalue with respect to A0. A0 has an eigenvalue, has eigenvectors. The eigenvectors of A0 are called k, and then the creation operators, an arbitrary combination of creation operators, act on it to produce the Fock space. And it's not difficult to count how many states there are, because you see the negative A's all commute with one another. The only non-trivial commutators involve a positive mode and a negative mode. So the negative modes always commute with one another, and therefore you can basically comb these negative generators. You can organize them so that the less negative ones stand closer to the ground state than the more negative ones. So you can always assume without loss of generality that M1 is bigger or equal than ML. And then it's sort of not difficult to enumerate what this Fock space is. And this is just the usual Fock space of the A's, and you do the same thing for the A bars. And the A's and the A bars basically live in two different universes. They don't talk to each other. The only place they talk with one another is that the ground state is shared. So if with respect to the left mover, A0 has eigenvalue k, then with respect to the right mover, well, there's no separate A0 bar. A0 is always A0. So with respect to the right movers, it'll also, that's also this. You always have to have one k, but on this k, you have arbitrary left movers and arbitrary right movers, but you can think of them as being a tensor product of the left moving degrees of freedom times the right moving degrees of freedom, and I'll only be in the following mostly discussing the left moving degrees of freedom and not worry much about the right moving degrees of freedom. And then, so the case can in principle be either discrete or continuous, but doesn't really matter. So there are, if the boson is non-compact, then k will be a continuum. If the boson is compact, then the allowed values of k will be discrete. But again, for the following, that will be an issue that we'll get in later on. And so they are what they are. And if you choose k equal to 0, that's the true vacuum. The true vacuum where also the A0 value has eigenvalue 0. Okay, so that's basically the sort of quantization of this theory. And now what I'll explain to you next time is we want to make sense of these modes. Now, obviously, here we have to start being a little bit worried because now they've stopped being commuting with one another, so we have to normal order them. And then we have to ask how the normal ordered modes act on the fields, and then what the commutators of the normal ordered modes do among themselves. And I'll explain to you that that leads to the Virasoro algebra. And it leads to the Virasoro algebra not by a matter of choice, but by a matter of necessity. It's not something you can sort of circumvent. It's what this problem teaches you it has to be. And so that's what I'll explain to you in the afternoon. And then I'll explain to you probably a little bit the free fermion. So this is the free boson theory. Then the free fermion is the other simple bosonic, simple conformal field theory, free conformal field theory. And then we extract from that and try to understand more generally the structure of a conformal field theory. And what I'll concentrate on will be the holomorphic fields, the fields like the stress energy tensor, and I'll explain to you the structure that these holomorphic fields obey and the many identities we can derive from them. And that's a very powerful and useful way of organizing the conformal field theory, and that will allow us to understand much of the structure. But that's it for now.